First, we are going to see the properties of negative feedback amplifier. So the properties of negative feedback amplifier under this, first is desensitivity of gain. So what do you mean by desensitivity of gain? It is nothing but desensitivity is a reciprocal of sensitivity. So 1 by sensitivity. So sensitivity, how to calculate the sensitivity? Sensitivity is nothing but ratio of fractional change in amplification with feedback to fractional change of amplification without feedback. So DAF by AF divided by DA by A. You all know that we have already calculated AF. What is AF? A by 1 plus A beta. So A by 1 plus A beta. So here while calculating the desensitivity of the gain, the transfer gain is not constant. So it depends upon some other factors. What are the factors which affects? So in EC1 we have studied the factors. So that is a Q point. What is Q point? Operating point with respect to temperature. So stability, how we are going to provide stability? By means of providing negative feedback to the amplifiers. So first sensitivity. So sensitivity DAF by AF by DA by A. What is AF? A by 1 plus A beta. Now differentiate AF with respect to A. So you have to use U by V method. What is the U by V method formula? VU dash minus UV dash by V square. So U we are going to take it as A and V is nothing but 1 plus A beta. So differentiate AF with respect to A. So DAF by DA is equal to VU dash. V is nothing but 1 plus A beta into U dash is 1 minus A into what is V dash beta divided by 1 plus A beta the whole square. That is V square. So 1 plus A beta minus A beta by 1 plus A beta the whole square, which is A plus A beta minus A beta gets cancelled. So at last you get DAF by DA is equal to 1 by 1 plus A beta the whole square. So here next is multiply the value, multiply this with respect to AF and divide by AF, right, to get the sensitivity. So DAF by DA is equal to AF by 1 plus A beta the whole square into 1 by AF. So DAF by AF is equal to what? DA by, I am converting the DA, taking this DA to here and AF here. So you can change it. So DAF by AF is equal to DA by 1 plus A beta whole square into 1 by AF. So DA by 1 plus A beta whole square into 1 by what is AF? A by 1 plus A beta from the previous equation, right? So DAF by AF is equal to DA by A into 1 plus A beta divided by, this will go to the numerator and this will be in the denominator. So DA by A into 1 plus A beta by 1 plus A beta whole square. So DAF by AF is equal to DA by A into 1 plus A beta the A beta. So 1 square and 1 term will get cancelled. What is sensitivity? DAF by AF by DA by A, which is DA by A into 1 plus A beta by DA by A. DS is equal to 1 by 1 plus A beta. What is D sensitivity? 1 by sensitivity. So 1 by 1 plus A beta. So 1 by 1 divided by 1 plus A beta is what? D is equal to 1 by, that is 1 plus A beta. So next is bandwidth improvement. How to improve the bandwidth? So the bandwidth is improved by means of the formula, that is we are going to calculate the low gain of the amplifier with the low and gain of the amplifier with high frequency and gain of the amplifier at mid frequency. So you can write it as AF mid equal to A mid by 1 plus A mid beta. In place of A you are going to substitute as A mid, and in place of A you are going to substitute for low as A low by 1 plus A low beta, and AF high is equal to A high by 1 plus A high beta. Name it as 1, 2 and 3 equations respectively. Now you are going to calculate the bandwidth. What is bandwidth? Upper cutoff frequency minus lower cutoff frequency. So higher frequency FH minus FL. You can write it as BWF with feedback as FHF minus FLF. So now I'm going to assign this equation as 4 and 5. Now we are going to calculate the force, that is in equation 5 you're going to calculate HF separately and LF separately. To calculate LF first, you're going to take the lower cutoff frequency with feedback. So A low is equal to A mid by 1 minus J into FL by F. That is, name it as 6th equation. So AF, substitute 6 into, already you know the second equation. What is the second equation? A low. So A low equation, what is AF low? Which is A mid by 1 minus J into FL by F divided by 1 plus A mid by 1 minus J into FL by F into beta. So take LCM, you get this. So A mid by 1 minus J into FL by F divided by 1 minus J into FL by F plus A mid beta by 1 minus J into FL by F. So this I can write it as A mid divided by 1 minus J into FL by F plus this I can write it as A mid beta. Now I can write it as AF low is equal to A mid by 1 plus A mid beta. This two terms, real part separately and imaginary part separately. Now divide this equation by 1 plus A mid beta. So you get A mid by 1 plus A mid beta divided by 1 minus J into FL by F into 1 by 1 plus A mid beta. So this represents AF low is equal to AF mid by 1 minus J into FLF by F. So what is FLF, which is FL by 1 plus A mid beta. Right, up to this clear? Now we are going to see the upper cutoff frequency. To calculate the upper cutoff frequency or higher frequency, which is FHF. What is FHF? AF high. AF high is A high by 1 plus A high beta. Name it as equation 7. So from equation 7 you can write it as from equation 3 you can write it as A high equal to A mid by 1 minus J into F by FH. In previous low you can write it as what? A low equal to A mid by 1 minus J into FL by F. Here for high, to calculate the gain at higher frequency, A high equal to A mid by 1 minus J into F by FH. Right? So substitute 7 in 3. You get AF high equal to A mid by 1 minus J into F by FH divided by 1 plus A mid beta by 1 minus J into F by FH. So take LCM and divide this equation same like lower frequency, divide by 1 plus A mid beta. You get A mid beta by 1 plus A mid beta by 1 minus J into F by FH into 1 by 1 plus A mid beta. So this you can write it as FHF equal to FH into 1 plus A mid beta. But in terms of previous equation, FLF is equal to FL by 1 plus A mid beta. In this high equation you get FHF equal to FH into 1 plus A mid beta. So substitute this, you get this. So you now we are going to represent what is bandwidth. What is bandwidth? Bandwidth is nothing but BWF equal to BW into 1 plus A mid beta. That is bandwidth with respect to feedback is equal to bandwidth into 1 plus A mid into bandwidth. So multiply A mid on both sides, that is AF. So AF into bandwidth is equal to A into bandwidth. So bandwidth you can write it as FHF minus FLF. What is FHF equation you have calculated with respect to FH and FL? So 1 plus A mid beta into FH minus FL by 1 plus A mid beta. So this is the diagram which represents the effect of negative feedback on gain and bandwidth. So you're going to take frequency on the x-axis and gain in the y-axis. So in the frequency you have, you can see the two curves. So first one is what without, that is without feedback, and next one is with feedback. So this is the bandwidth. So for the bandwidth is nothing but upper cutoff frequency minus lower cutoff frequency, and this is bandwidth with feedback. This is bandwidth without feedback. So this is A mid, and this is you are going to divide with respect to 1 by root 2 for getting 3 dB line. Okay, so 0.707 A mid, and this is AF mid, and this is AF mid for the second one. So 0.707 A mid. Next is you are going to study the reduction in noise, which is the fifth one. So what is reduction in noise? How the noise is reduced? So you're going to take an amplifier A and you're going to connect a noise component, which is VN. VN is a noise source and one is signal source. This is signal source and this is noise source. So signal source I'm going to write it as Vs, and noise source I'm going to write it as Vn. So input signal is nothing but Vi and output signal is nothing but V0. So what is Vi? What is Vi? Vs plus Vn. Vs is signal source and Vn is the noise source. And the negative feedback, when you are giving negative feedback for the amplifier design, it improves the signal to noise ratio. So first for this, for instance, I'm going to take a noise free amplifier circuit and a noisy amplifier circuit. What is noise free? That is free from noise. And what is a noisy amplifier? It generates noise, right? So this kind of amplifier I'm going to take. So first in this signal to noise ratio is nothing but Vs by Vn, right? Vs by Vn. What is Vs? Signal source. What is Vn? Noise source. So here I'm going to calculate the noisy amplifier and noiseless amplifier. For the noise free amplifier, I'm going to write the gain of the amplifier as AF1 and AF2 with the second amplifier. So AF1 equal to A1 by 1 plus A1 beta. AF2 is A2 by 1 plus A2 beta. You all know that AF equal to A by 1 plus A beta with respect to that first amplifier and second amplifier. Now you have two sources. You have studied the superposition theorem in the circuit analysis. So how to use the superposition theorem. If one source is acting, you can calculate with respect to the first source. Second source will be what? Short circuited. And when you're calculating second source, first source will be short circuited. So V0 is equal to output, V0 is equal to Vs. Okay, Vs signal source into A1 A2 by 1 plus A1 A2 beta plus Vn into A1 by 1 plus A1 A2 beta. Now if you are just assuming to calculate the gain of the first amplifier and second amplifier, just A1 is assumed to be 1000, A2 assumed to be 100, beta as a reverse feedback factor, that is feedback gain, that's nothing but beta, which is 0.01. So apply here, AF1 is equal to A1 by 1 plus A1 beta. What is that? 1000 by 1 plus 1000 into 0.01. The value was 90.9. So AF1 value was 90.9. Next is AF2, which is A2 by 1 plus A2 beta, which is 100 by 1 plus 100 into 0.01. So AF2 was 50. So with respect to that, we are going to estimate the signal to noise ratio Vs by Vn, which is into A2. Here, when you apply the values, you get A1 A2 by 1 plus A1 A2 into beta by Vn into A1 by 1 plus A1 A2 into beta. So A2 alone you have, remaining all the terms gets cancelled. So the signal to noise ratio is Vs by Vn into A2, right? Next is distortion. How to eliminate the distortion? For example, if an amplifier, you are having an amplifier which have the amplifier without feedback and amplifier with feedback. When you have negative feedback, this is the curve, and when you have the amplifier, designing amplifier without feedback, this is the curve. So DF or AF, which is equal to A by 1 plus A beta. Here DF is equal to D by 1 plus A beta. Assume input source Vi is 5 volts, Vf is 10 volt. So what is V0 from that? Vi minus Vf. So what is Vi? 5 volt minus what is Vf? 10 volt. What is the difference between this? 5 volts. So 5 volt minus, that means negative. It won't be negative. So V0 is equal to plus 5 volt. So this is the linear characteristics and this is the non-linear characteristics of the amplifier. So before going to the next topic, so the next topic is nothing but types of feedback amplifier with different topologies. We want to know what is a voltage amplifier, what is a current amplifier, what is a trans resistance amplifier, and what is a transconductance amplifier. So voltage amplifier is otherwise called as voltage series amplifier, voltage series feedback, or series shunt feedback. We want to know what is series and what is shunt connection. So the input is here, this connection is nothing but series connection, and this connection is nothing but shunt connection, which is connected across. Across means shunt connection. So voltage amplifier, the amplifier A you have, beta you have, nothing is there, just amplifier A and beta. For amplifier A input, you are going to give the series connection. This is the series connection, and this is the shunt connection. This is the output resistance RL. So here what you are going to calculate here, A is equal to V0 by Vi. Vi is nothing but equal to this. So V0 by Vi. And next is current amplifier. What is current amplifier? It is otherwise called as current shunt or shunt series feedback. So shunt series means what? Shunt is connected at the input, series at the output. So shunt means across, input across with respect to a current source. If you are using, that is a current amplifier. Voltage source means what? Voltage amplifier, right? So here current shunt amplifier is otherwise called as shunt series feedback amplifier. So both are current, input and output both are current. So it is a current amplifier. Next is trans resistance amplifier. It is otherwise called as voltage shunt feedback amplifier or shunt feedback amplifier. So for the trans resistance, so you're going to take input as what? Current, output is voltage. So input is Is, output is V0. So next is transconductance amplifier. So you have input and output. Input is Vi, output is I0. Both are in what? Series connection. So here both are in shunt connection, here both are in series connection. So it is series feedback amplifier. So we want to understand the voltage amplifier with series feedback. For that you have learned basically how to apply Thevenin's theorem, how to apply Norton's theorem, right? Next is we are going to learn the types of feedback amplifier. Before going to the types of feedback amplifier, we want to know what is the, how to represent the feedback amplifier. So to represent the feedback amplifier, first I am going to explain what is the voltage amplifier with voltage series feedback. That means input what you are going to do, output what you are going to get. So for the input I am going to use series mixing. I told you that when I am explaining general feedback network, so you have the mixer, that is mixer network. So here I am going to use a series mixer. Output I am going to use the shunt, that is a voltage sampling. So here this is the circuit diagram. Here for voltage amplifier, this is the feedback network. This amplifier is general. Here if I am going to denote a voltage amplifier, means here it is a voltage amplifier. So here it is a feedback network. So input I am going to use series mixing, output I am going to use voltage sampling. First apply the get the Thevenin's equivalent circuit. So for Thevenin's equivalent circuit, here it is being an voltage controlled voltage source. I am going to take the voltage as Vs, source voltage Vs, then source resistance Rs, then input is Ri, right? Ri is the input resistance. And voltage amplifier, what is the output of the voltage amplifier? It will have AVVI. You can say it as V0 is equal to, that is A is equal to V0 by Vi. So I can write it as AV into Vi. So output resistance is R0 and load resistance is RL. Here Ri is very greater than Rs and RL is very greater than R0. So V0 is proportional to Vi. What is V0? V0 is nothing but output voltage. What is Vi? Input voltage. So V0 is nothing but AV into Vi. What is AV? V0 by Vi. Next, here I am going to take it as Vi and Vs both are equal, because Ri is, when I consider Ri and Rs, Ri is very greater than Rs. So I am going to neglect the Rs. And when I consider RL and R0, R0 is neglected, right? So R0 is very high. So I am going to neglect that. So AV equal to V0 by Vs. So for an ideal voltage amplifier, Ri value is infinity and R0 is 0. Next we are going to learn the current amplifier. So for the current amplifier, this is the diagram. So this is the current and feedback network. So current amplifier, I am going to take a current amplifier. So current amplifier with respect to feedback network beta. So here the current shunt. Shunt means what? Is with respect to Rs. So Is and Rs both are connected in shunt connection. And the output here, I am going to use the current sampling. Okay. So here it is the CCS, which is current control current source. So the output current is proportional to input current. I0 is proportional to II. So I0 is equal to AI into II. What is AI? I0 by II. This only I am going to derive by means of using Norton's current. Means how will you find the current? By means of Norton's theorem. How will you find the voltage? By means of what? Thevenin's theorem. So here Norton's theorem, Is, short circuited current Is with respect to Rs and Ri, both are connected in series, and then AI with AI into II into R0 RL. So output is V0. So Ri is less than Rs. So Rs is neglected. RL is less than R0. So R0 is neglected. So next is AI is nothing but what? I0 by Is. Here it is Ri is equal to 0 and R0 is infinity. Next is trans resistance amplifier. So for the trans resistance amplifier, Is is a input current Is and Rs is the resistance, source resistance. Trans resistance amplifier, output is nothing but voltage sampling, input is shunt sampling. So both are shunt connection. So Rm is equal to V0 by II. So how to get this Norton's equivalent circuit from the input side? Thevenin's equivalent circuit you are going to apply at the output side. So what is the combination of the trans resistance amplifier? Output voltage by input current. What is output voltage? V0. What is input current? Is. So V0 by Is. Next is transconductance amplifier. So the transconductance amplifier, so this is the transconductance amplifier. So you are going to take Rs with respect to Vs, and here you are going to write the current sampling. Here it is a series mixing. So this is the current control voltage source. So output current is proportional to input voltage. So I0 is proportional to Vi. So I0 is equal to Gm into Vi. What is Gm? I0 by Vi. So draw the diagram. Input you are going to use the Thevenin circuit. Output you are going to use same Thevenin only, because it is a transconductance. Here in terms of conductance I am going to write. So I am going to use the Gm into Vi. What is GM? I naught by Vs, right? So for the ideal amplifier, current transconductance amplifier, Ri is infinity and R naught is also infinity. Next, this is the small characteristics. This may be asked in 2 marks. So the input resistance Ri, output resistance R naught, and transfer gain. So infinity 0. Whatever results we got, what is Vi, V naught, all those things, I'm going to write it. So both are 0, infinity and 0, 0, infinity, infinity, 0. And what is the voltage gain? AV, V naught by Vs. Next, AIS, I naught by Is. What is GM? I naught by Vs. What is RM? V naught by Is. Right? So if you study this, then you will understand easily. You can understand the next important question, which is